Hi, everyone. Thanks for coming. I'm Saksham. I'll be talking about reflection today. The title is more like whimsical.
Speak up, 'cause there's no microphone. There's no microphone.
Oh, right. Oh, yeah. All right. So I'll be talking about reflection today. And the title here is a bit whimsical. The general feeling that I'm trying to convey here is reflection makes for really good libraries and a really good code experience for your users. So before I get started, just a little bit about me. I work as a director of quant research technology at Tower Research Capital. It's a hedge fund based out of New York. I develop low latency trading systems where nanoseconds and microseconds are like common terms, and high throughput research systems in C++ and Python, large, big data. I talk a lot about Python and C++ generally. Last year I was talking about Python bindings in this exact room. I like clean APIs and I like clean software. I don't like overcomplicating things too much, especially because I like to have other people be able to. My job has users of my code often are not the most expert at C++, so yeah, I like simple software.
Can you speak a little bit louder, please?
Okay. All right. And I think the one other part is all the contents here are mine. So if you want to talk about anything, talk to me, not my employer. All right. So a quick overview about what we're going to talk about today. There's a background section in this talk, which I've kept at the start, which is, I know that there was another talk about reflection earlier in this week at this very conference. I won't assume that people have gone to that. So there's going to be some background about it. And then there's going to be some work on, some slides on 3 different reflection usages in the real world that I tried to end up implementing. They work on my laptop using some experimental compilers, so they're not really pipe dreams. And finally, I'll spend some time talking about how we've been living without reflection for so long, if it's such a cool thing and nice thing to have. All right, so yeah, let's get started. And I'm going to have a lot of space-related images here. They're all generated by generative AI. The metaphor holds for some time, like reflection. All right, so I tried to come up with a clean definition of reflection, and I think every paper has a different definition, so I don't think the semantics matter too much. But what we really want to do is we want to talk about the code that we've already written in some way. We want to operate on it. We want to find out something about it. We want to mutate it, perhaps, hopefully. This would be like it would be cool if we could do that, right? Just be able to print some members of your class. It sounds like it's similar to metaprogramming. And so why is this a new thing? Like, why did we give this a term? Again, I tried to think a lot about this. There's not really a good answer. They're similar in spirit, except that you could imagine that operating on const expr values instead of using types to represent every information about your code can change the feeling of your code. That's still a syntactic difference, right? Like, just saying that, oh, instead of types, we're going to have const expr values, that's not changing anything semantically. But the reason why we're talking about reflection today for CPP 26 is if you implement this as a clean bag of features, your compiler can actually put richer and easier to use information in this bag of reflection. So you don't have to jump through a bunch of hoops and implement some ad hoc metaprogramming features in the language that don't necessarily, they try to provide you reflection, but in an inconsistent form. So reflection is like this bag of features that, this is how I'm seeing it. There's just a bunch of things in there that all compose well with each other really nicely. And yeah. Okay. Why is this not going forward? Okay. All right. So what exists so far in a lot of languages is this thing called runtime reflection. like this is a Python snippet. Like you can go over the members. This is similar to what we just saw as like that dummy C++ API. You can just go over members at runtime. Obviously, this is Python, so it is runtime. And this works. And it's like a neat abstraction that a lot of non-performance focused languages actually just include by default, and people like it. Like you're able to build pretty cool tooling with this. The pipe dream here is to have this static reflection or compile time reflection. So in C++, you would ideally want this code to have been resolved at compile time. So there's no like if checks and for loops happening at runtime here. The compiler knows everything. We should be able to do it. So how to design that? Before we decide how to design that, I want to take a step back and just look at the ecosystem a little bit before we go into making up our mind on how C++ should be able to do it. So we just saw Python, right? It's super flexible. In this language, everything is an object or a type, and you can just go in there and change anything. You can change what a function means. You can add new members to a class. You can remove functions from a class. You can just do anything at runtime. Obviously, that's super crazy. We don't want to be doing that in C++. But just to illustrate the power, so we can imagine the world that we could get into, I tried to write a snippet here where we have a function called modify class. It takes the copy method of your class, it wraps it with some extra stuff, and gives you a new class. And it works. And you can also just go and print all the members of your class here. This is all runtime code. Hopefully, in C++, we would be able to do this at compile time, but it's good to know that we could do this in some other languages. The other language I like talking about is Golang. It's closer to C++ in some respect, except for the fact that they also chose to do some sort of runtime reflection. Some people might be reminded of RTTI on this, but it looks very similar to Python when we see the code. But before we jump into the code, I just wanted to take a side segue into this thing where I wrote this term called duck-typed. Like Golang is a duck-type language. And this is something I'm going to be hearkening back to later in the talk, so I just want to take a moment to talk about it. What does duck typing mean? So I have an example here, basically. So as you can see, you have two implementation classes here, essentially, car and truck. They have this method called start. There's an interface vehicle, which also has that method start, but the car and truck never actually directly inherit from it. It sounds a little bit like type erasure or perhaps concepts. Like concepts actually kind of let you do that, right? Like you can do that at compile time, that I need these functions. So in Golang, people either call this structured typing or duck typing. And this is what I would mean by duck typing as we go forward. Just if it quacks like a duck, might as well be called a duck. OK. So coming back to reflection in Go, here's a snippet where we're able to print out all the members of a struct that was provided here. And this is the simplest reflection example in Go. It also has its own vocabulary, so don't worry if you don't understand what value type or LM and all semantically mean. But all we care about is that we're able to go over the struct and enumerate. And this is happening at runtime because we're doing prints and stuff here. Golang does not have a compile time expressive metaprogramming language, so that's what they have. There's more cooler things in Golang that we'll introduce as we get to them. And finally, a little bit about Java. This, again, surprise, surprise, also looks very similar to Python and Go. It's going to be runtime. Obviously, it's inside a VM, which is running everything at runtime. So you usually just have access to all the types at runtime. As you can see, we're able to loop over all the methods of that class. You get a list of this class called method. So this is a new thing we didn't see in Golang and Python before, that there's this type that you get for these entities you get returned from these reflection-like methods, right? there's also these class parameter types. So all the parameter types of M are actually objects of this type called class. So some stuff is typed here. That said, it still looks and feels pretty much similar to the runtime reflection we saw in Python and Go. All right, so what do we do if we try to get this in C++? Gets scary, right? Like, we're trying to introduce some very crazy introspection features into your code. Like, you could imagine you can access private members of a class with it or something like that. It's all like a scary notion. Also, runtime is anyway something that people kind of steer clear of. Luckily for us, or unluckily, C++ has this thing called zero-cost abstractions, right? We all love that. We all did not like it when RTTI broke that. The thing is, our language is so Turing complete at compile time that we could probably lean on it and envision a world where this works. And turns out it does. After so long, we finally do have a new hope. I mean, this is probably one of, I don't know, the 10th paper talking about reflection. But for the second time, people are getting quite excited about reflection. So P2996 is a promising paper. It's been discussed. It's been discussed in a bunch of committee meetings recently. It's gaining a lot of traction. And the best thing is, it has two really good working implementations already. One by Edison Design Group and the other by Bloomberg. They forked out Clang. So 2 working implementations is actually a pretty good sign. So hopefully, we're getting there. There's also some good consensus on syntax and semantics. People have been debating these for quite some time, and it looks like we're settled on these things. There's also some interesting choices made which are a departure from some earlier versions of reflection as proposed, for instance, by Reflection TS by David Sinkel back in 2021, I believe. All right, so what do we have in this paper? The first thing we got is this magic thing, like this unary operator, the caret operator, which lifts things into reflection land. It's kind of poetic, right? Like, you have something in your regular code land, and then you lift it into a reflection land. It can lift functions, variables and friends, non-static data members, templates, constants, even namespaces. Something that template metaprogramming usually doesn't talk about, into a dreamy world called reflection. Okay. When you do lift something into reflection land, what you get is this std info, which is this formless scalar type, which describes everything there is to know about the thing you just reflected. For all we know, it could contain pointers to internal data structures inside the compiler that let you access information about the thing you reflected. But that's not part of the standard. That's part of the implementation. We also have this other thing called the splice operator, which takes a std info and kind of puts it into your code in a way that you could imagine in macros you're used to. When you invoke a macro inside your code, you're kind of doing something else somewhere else, and then you're putting it into your code. So this is the language equivalent of that, essentially. It does require the thing you're splicing to be a constant expression, which is interesting, and it shows up in various contexts. Next up, we have this thing which is very controversial called define class, which a lot of people would want. You know, we want to be able to construct code on the fly, but it's also one of the most controversial features because it can introduce new ways to do, as was pointed out earlier, it can introduce new ways to do stateful metaprogramming, or it can allow you to inject new code, which is just a new thought to be comfortable with as C++ programmers. The syntax is not the best at the moment. You kind of have to put a static assert there for some reason. It is what is the least path of resistance forward so far. It might change in later implementations. Anyway, so what we just saw can translate to this thing. And you can imagine that this is pretty good. We could do a lot of things with this. We could let users define a DSL that this is what I want, and we could construct structs on the background which do the thing that the users described. And finally, we have a lot of const-eval methods to go with this. There are way too many methods to put on any number of slides, so I just picked out a few of my favorite ones. You can get names of different things you reflected. You can get functions, and you can check what kind of thing you reflected. You can loop over members of a class, and so on. All right, so we kind of claimed that we need all this, but do we really? So the paper has a lot of really simplistic or advanced examples. I don't want to go over all of them, so I'll just go over a few of them in rather quickly, just to make sure that everyone is on the same page. So the most favorite example for everyone is just enum to string and string to enum. I don't know since when my libraries have had protobuf, partly because I want to convert strings and enums to each other, and I don't want to type out every single thing every single time. And luckily with this proposal, we're able to do that. It's not that complicated. I have a template for there. It doesn't have to be there, but let's let that be for a moment, for now. Hi, yeah.
Yeah, so I went over this slide in my talk yesterday, and it came up, right, because I used the Godbolt version of it. When you go to the Godbolt link that's associated with this, the template 4 is not there because, of course, that's not part of the standard.
Yeah.
So there's a thing there called expand, which, who knows? So just everyone be aware that the implementations that are out there right now are, they're sort of on the cutting edge, and they're sort of alpha, maybe beta, I don't know.
Yeah, especially this template 4 thing is, there's some workarounds for this in the library. They are workable. So far, I've been able to do everything I wanted. It does take a bit getting used to, because mainly the issue being that the loop variable is not const expr usually in a for loop, even though the thing on the other side of the colon is. So there's something called expand, which is literally a line, just a replacement of this line. And it kind of works, not entirely, but kind of.
But where does expand come from? It's just something that they built into the compiler?
No, it's just like a 15-line function.
In the experimental meta header file,
okay.
Yeah.
It comes with the EDG.
So the EDG one has that. The Clang one doesn't have it right now, but the snippet that they use is in the P2996 paper. So I just paste it at the top of every code that I'm compiling, and it just works.
I see. Okay.
Yeah. Yeah.
One more thought.
Yep.
Here, of course, this problem is well solved in Magic Enum is a library that does this extensively. So if you're not familiar with that library, go take a look at it.
Is that a C++20 library or?
No,
Oh, that's cool.
I think it will work with 17 and above.
Nice. I was looking at Boost ext reflect yesterday, and it uses source location and a few other things to also solve this problem. But
Yeah, I think
yeah.
that might be how Magic Enum is.
Yeah.
But all those existing solutions, unless I'm mistaken, have severe limits on the number of enumerators you can have in the enumeration, because there's no equivalent of enumerators of.
Yeah.
So they have to basically search the entire state space.
Yeah.
Yes, there are issues.
Yeah.
I agree.
Even the Boost ext reflect one that I saw, it just had a function copied 75 times for 75 different lengths of enumerators. And again, it worked for most practical purposes, but it's good to have things in the language. So as I said earlier, all these reflection things are basically, the way I'm seeing them is, it's like a bag of clean things that work well with each other. They might be solving things that could be solved hackily earlier, but if we have a clean framework to add new features in, we're probably going to be better off as a language. Yeah. Another thing that the talk had was this very simplistic command line parsing example. If you have a struct and you just want to parse some command line into it. There's a working implementation of this parse options that's totally not complicated. Also, the same template for thing applies here. You could replace this with the expansion statement. that said, this works with this example, like with this working paper. The one other thing I want to say about this is I see command line parsing quite similarly to data deserialization. There's just some input coming in and you want to put it into some structured form. So one can imagine that the same principles would also work for serializers and deserializers, which is a cool thing. Except for the fact that we glossed over the issue here. The user might also want something like -f to work, like a short form, or they might want a help string or something. The paper also has an option for that. I'm not going to show the implementation of this because A, it's in the paper, and B, it's a little more complicated. But this also works with this reflection proposal that we have. The idea being that you let the user customize a few things in their input, and then you can construct the thing out of it. All right.
Quick question.
Yeah.
Can I go over attributes as well? Because I much prefer a declarative style, so I could slap an attribute on it and then.
You want to put attributes onto this thing?
No, instead of doing an option class,
Yeah.
I'd rather have an attribute that says like, well, here's a short form, whatever, more the Rusty style.
Right. So
Could I do that, or is that?
That's a separate paper that a lot of people who've been trying to use reflection have noted that would be nice to have. It's not there yet, and blocking reflection on it would not work.
Oh, no.
There's also a workaround. So this is one workaround. There's also another one, which is like having a customization struct, which just uses like class template overloads to get your customizations to get picked up. But yeah, which is why I didn't want to go too much into this. But the thing is, like, we can also do this more powerful thing here. And one or two more simple examples. You can obviously just loop over classes members and construct your own description of the members. This is a const eval function that's kind of required. Or you can go over an array of structs and you can convert it into a struct of arrays. People like that. I think it's because you want to expose a clean DSL to your users. Users should not have to worry about how they arrange, how you are going to arrange the data for them. So, but you could do that with this thing. So, all right. So enough about the examples. The one thing that a lot of people also end up talking about is, why is this std_meta info thing just this one opaque thing? Like, why not like a whole hierarchy of classes? Std_meta method, std_meta variable. This sounds nice. It also sounds intuitive. It also sounds tempting to use template specializations with these. But for various reasons that we'll get into, we decided not to go this route and instead rely on ranges and algorithms. Hannah?
Actually, we didn't decide to not do that. We still open in future. Maybe it will go there.
Fair.
That's the status program.
Yeah, I think the paper also has some ways to make these things kind of work. Like, it has these meta type things, but again, the whole reasoning, like one of the reasonings that came up earlier was this thing that if you have too many types, the things get slower to compile. And one of the earlier papers, 1240, had an example about this. This is an example pulled directly from the paper, and I tried compiling this on my laptop as well. Like, on the left-hand side, you just have integer types, and on the right-hand side, you have a wrapper around the integer. So you're just constructing some extra int classes. And on my laptop, the left-hand side takes 1.4 seconds, and the right-hand side takes 2 seconds to compile. In the paper, it had 0.6 and 1.2. Yeah. The general feeling seems to be that it's slower to compile if you have a lot of types, which is understandable. But I think the main reasoning that a lot of people have been banking on right now is that the language could become more rigid if you started going down this class hierarchy route, because you won't be able to change the meaning. Like, the users might start just writing functions where they're like, okay, if this is a variable, then this is the specialization to be picked. And you won't ever be able to change the meaning of a variable in the future in the language. And apparently that was done in CPP 11. So there is some scare related to that. What this paper is going for is that users actually just write feature-gated code, where if you're going to use something's members, then you just check that if that thing is a class, then you go and look at the members, otherwise you don't. So kind of like duck-typed code, that instead of just expecting the compiler to catch it, you check the features that you want, and then you use it. So that way, at least there's a forward and backward compatibility scenario that could work if the language ever wanted to evolve and change the meaning of some class or some something like a variable or a class or anything. So it just makes people feel easier, I guess, more comfortable. Yeah. All right, so now that we know this, what have we seen so far? We saw 4 languages, and the interesting story that happens here is that C++, among the languages we saw, is the only one trying compile time. That said, Carbon, dlang, and Circle also have compile time reflection, but they chose to go the type route. I'm not the most familiar with those languages, which is why I didn't want to put them on the slides. C++ is trying this value-based thing first. Hopefully this works out for us. All right, so now done with the background, getting into the library part. So how do we want to use this? Like, we've added a cool language feature, but what do we want to do with this? Like, we don't expect users to be able to write this complicated code. So the obvious answer is libraries. The hope is that we'll be able to make C++ library ecosystem much more friendly to users. We'll be able to write DSLs for users. A command line parsing library would no longer need to ask users to implement the same thing like at 3 different places, like name all the members and put the parsing code and name the thing again when you're writing the string for it. It's just general boilerplate reduction. So on this topic, I ended up working on like 3 different library ideas while I was getting into this whole reflection thing. The first one being Python bindings, which actually I started working on this after the paper P2911 by Adam Lack and Jagur Dave from Bloomberg. They ended up using an earlier version of the paper, and I think we ended up having the similar experience. The idea is that you can have some code on the right-hand side. For instance, I have this C++ class and a bunch of other classes, and I want CPython to be able to get a Python object corresponding to the C++ class. For anyone not familiar, C++ and Python can run in the same process, so we are going to be talking about basically intermodule data sharing in this case, like 2 different shared modules just communicating, essentially equivalent of that. Okay, as of right now, what we have to do is we have to write the thing on the right here, which is more or less a copy of what we just had in the C++ side. There's some nuances here, like what to do if the function's return type is a reference, or how do you name a type in Python, because the C++ type name might not be very idiomatic in Python, for instance. But let's gloss over those for a moment. What we want is, we want reflection to be able to generate the thing on the right without us having to worry about it or duplicate the whole thing. It kind of makes it easy. So let's dive into it. The idea being that we could create a function that is able to do this now. First, we declared the type object for the Python binding library. This seems easy. The only thing we have to use here is get the name of the class. Of course, there were other ways in the language before to get the name, but now we're going to use reflection, obviously. The second thing is we need to loop over all the members of the class. They could be functions or they could be non-static data members, and we want to provide accessors in the Python type to access these things in your C++ type. So obviously, we need to loop over the whole thing, right?
Just making sure the return type object, that's a Python object that we're
Yes.
defined with our C++ type code, correct?
Yes, so this is a Boost Python implementation, and Boost Python has this RAII wrapper around Py object, which is this object. It works pretty nicely. Yeah, so we ideally want to loop over all the members of this class. As mentioned earlier, template for it doesn't exist. luckily for us, this is the expand statement we alluded to earlier. This does work. So with that in mind, we can also look at this thing called, now we probably don't want to expose private methods from the class to Python. So we're going to skip over those as well. And this is basically the meat of it. The way you write Python, the way you expose C++ non-static data members to the Python type is you provided these pointer accessors to your non-static data members. Except for the fact, how do we get the non-static data member that we're looping over? It's going to be that splicing thing that we saw earlier. We already had a reflection reference to that. We had a reflection to it, so we can just splice it in. And this also works. And finally, we want to take out all the non-special functions, like your class might have some methods. And for now, I just excluded all functions that had any reference return type. You can write any arbitrary metaprogramming to do that. I believe there are some const eval functions that could also do that. I haven't tried stringing that together here. But after that, you can just mutate the type object again with a spliced version of that method function. And yeah, voila, that works. So this is the most simplistic version of this whole thing. The problem comes out when you talk about customization. As I think someone mentioned earlier, that what if you want to annotate one of your functions that even though it returns a reference in the C++ signature, I maybe just want to return a copy to the Python layer. Or maybe you want to actually return a reference to the Python layer, so you don't do an extra copy. Or maybe you have some function that has multiple overloads, and you might want to name those overloads differently. Or doc strings. Python has programmatic doc strings, and there's no way to expose these here. The answer to this is, as of this paper, this can't be done, except with like some external customization overloads. What you really want is, what you might want is something like this, right? This is user-defined attributes. People have been discussing this. We don't have this. What we do have is something like this, that you can keep outside of the original source code. You keep this where you actually run the binding code. And I agree this is not super DIY, but it kind of works. This would be ideal if you had control on the source code, which not everyone has. So I guess we have room for both here. But one fun version of all of this is something in Golang that just, I got reminded of this at some point. Golang has these structured programmatic attributes, which it uses really powerfully to write nice serialization and deserialization libraries. What you do is you write some key comma values in backticks inside your structs. And their entire ecosystem's libraries are based on these user-defined attributes, which are actually kind of structured. Like you can they're called tags, so you can just check the value of the tag required. And I think it's a very cool thing, like, especially given that how cleanly they've baked it into their library ecosystem. So it could be an end goal to aspire towards. So summary of the Python binding thing. Basic stuff we can do, but we would like some form of user-defined attributes. We might like them. Until then, we can do some customizations, and hopefully that gets us by for now. Right? Okay. Hi.
So is the idea behind user-defined attributes to be able to just slap additional meta info into the entities that we want to reflect on later?
Presumably, like you should be able to access the user-defined attributes in reflection land. But as of right now, since we don't even have user-defined attributes, yeah. But hopefully, if and when we do have those, we would want to be able to reflect on them. Like Golang's reflection does have that. I like that's a case in point, basically. I'm not saying we need to copy it, but it's a case in point and it works.
So in the currently proposed reflection, can we add or remove anything from the meta info object? Or is it all just what is currently provided by standard and compiler?
Kind of no, except for the define class thing. Like essentially, if you check the incomplete type, you reflect that, you'll be able to see an incomplete type as a reflection. Like that reflection would be the reflection to an incomplete type. But if you do a define class and then you do that, then it's a reflection to a defined class. Right. This is the other thing this is the thing that actually got me started into it. It's a little more complicated than the Python binding example. And to motivate what this is, what would you do if you had a hash to a type? Like I could just give you a hash that describes the layout of a type. I often need this. I'm imagining some other people also have needed this. The common use case is that you have two different modules that might have been compiled at different times, communicating with each other. Maybe there's no handshake between them. Maybe they're communicating over the network, over files, or within the same process. What we'd like to do is we'd like to do a compatibility check between their two schemas of the message, and hopefully not throw a segfault because the schema has changed and someone compiled with a new version of something and things have just gone to. Yeah. So what we want is some short schema type descriptor that is able to achieve this for us. As an example, like this is a real world thing that I run into sometimes. I have a bunch of publishers publishing different data schemas and they're publishing over UDP and there's some source code change that happened and now the schema has changed. There's no clean, like, easy way to just assert that they're talking about the same schema. Perhaps you want to put some human version string in there. Okay. Wait. Okay, yeah. So before I go any further, just quickly talking about why not just the text version of that type. Maybe I could just print the type there, right? I mentioned UDP there. I work in a financial services company, so speed is important. You can't really do that each time unless you have a handshake, like a TCP connection. So you could do that at the beginning. Or if size is important, which is also true on the network, or things written onto the disk. Since I'm talking about UDP here, I think a hash might work. I also have a different use case for this, and this is something that a lot of people have run into, surprisingly, which is you're trying to send the same type across two different shared module boundaries. As an example, I have two different modules here, libcreator.so and libusermodule.so. Both of them have the same source code for this myCLS. The left side has a function that creates this because perhaps that's what the implementer of the library provided us. And there's a Python binding for it. Python is just a glue here. It's just taking this thing, return value, and sending it to the other guy. The other guy is, let's say, you. You're trying to implement some use for that object that you just created. Would you be able to do it? Like, would a binding library be able to see that these two .sos, when they talk about this myCLS, are talking about the same thing? Probably not. So this is another place where I've often wished that we could just compare two types coming from two different places. If you had a unique standardized way, or even a library way, to say that this is how I represent this type. So that's where the idea for ABI hashing came from, that what if we had a standardized way to do this? And obviously, a simple version field doesn't work because in a large code base, that's just not going to scale. It doesn't handle compiler attributes, for instance, like someone might add an attribute somewhere without knowing. And it's just something that has to be done, like it's a promise from the user. Like a library cannot depend on your promise. Okay, so how do we actually do this type hashing? Of course, it's a decent test. It requires some sort of compile time hash function, and it also requires like full visibility into all the members and of your class. And it requires some sort of recursion as well. So we're also going to see recursion work here. There's no one-size-fits-all for a hash. So I decided to make a 1-byte struct for it, which is the hashing config. So people can have different hashes for different configs. It has some backwards and forwards compatibility guarantees. Not guarantees, but graceful checks. And this is the test case that I'm just going to cover. I have working examples with this. There's an empty class that just literally inherits from some other class. So we'll test if that works. There's some pointers in there. There's some bit fields in there, templates in there. So there's two ways to write this code. And this is where like the new value-based reflections interface shines quite a bit. You could have written code the old way with those template arguments. But given that this is value-based and these meta infos are actually just values, you can also write code this way, where they're just signatures. And the function is const eval. Dan Katz suggested to me this thing after I'd written it the other way earlier. All right. So to get started, first we just recurse over all the base classes of the class that we had. This P2996 provides bases off. And I haven't shown the hash combine function here. I pulled one off of Stack Overflow. It works at compile time, so I'm happy. We can just do a recursive call here inside the const eval function. It works fine. We also maybe want to ignore pointers if the user is sending the struct over the network. You might even want to throw an exception in this case, that why are you sending a struct with pointers over the network? One question that doesn't have a clear answer is, do you want to hash the name of all the members? And I think most people would say yes, just because the name encodes some semantic information in there. Like I might have a struct point with int x and int y. And if x and y get swapped around, like I probably want to invalidate the hash. Another cool thing in this paper is this bit offset off and bit size off. There's no const eval ways to access these this reflection paper. I actually tried making that work. There's some hacks. They didn't seem to generalize. Now we can actually access this information as well. Hey, yeah.
So you just mentioned like swapping the name order, for example, but how would reflection work with, let's say, non-pod types at this point? Because compiler is free to rearrange the names of the class.
If it's a non-pod type, you probably wouldn't be serializing it over the network, right?
Why not? We can still send data.
Fair.
I can also serialize it to a database or to a file.
Mm-hmm.
So I
feel like I'm still not seeing the issue though. So if you have two members in your class.
Yeah, I'm just wondering, what does reflection guarantee? Does it guarantee the order I have defined in the class, or the order after some sort of compilation when some optimizations will apply? Because then you kind of, your bets are off. Yeah, you cannot say like I will hash, and as soon as x and y come like in a different order, I will invalidate my hash.
It should be invalidated in that case, but
The offset of
Yeah.
will get you the
Yeah.
actual offset after the compiler has done all its magic on whatever rearranging it does of the class. So that is based, the offset of will give you actually the post compiler rearranging.
If I can perhaps reword that question, are there any guarantees on the order of the data members that are returned by that reflection function that has more guarantees than what we have for the data layout that's generated by the compiler? Or will that order returned by reflection also have the same, maybe reordered across different accessibility levels behavior that is currently permitted for compilers.
That's a fair point. I didn't see any mention of the order. That said, one could put a const expr sort based on the offset of.
So
And you could do that, but it's a good point. Yeah.
it's even possible I kind of have like version 2 of my library and I extend the object with some more data fields, but I can provide some sort of, let's say, conversion path from version 1 to version 2 based on reflection. So I still want to have something reliable. And this is like question how would I really put hash there or not?
Yeah, so in that case, I wrote a paper on this as well earlier. And in that case, I would recommend using a full textual representation of your type and having the other side. At the moment you start getting into conversions, then you're not talking about the layout equivalence, right? You're just talking about the two layers understanding each other. And that's also possible. I have a slide on that a little later. Yeah. But it's not going to be an exact one-to-one conversion, right? It's not like you can do a reinterpret cast on that, on the incoming data in that case.
To answer Ezra's question, non-static data members appear in declaration order.
Oh.
When you go get a members of or
Of reflection.
For data members with the same accessibility.
there
Or
it
did
is,
that
not-
change recently?
non-static data members appear in declaration order.
That actually has changed. They're specified.
Okay, so it changed recently.
Cool. Yeah, but of course the offsets are pretty important to hash here as well. And moving on from the offsets, then there's the part about actually going into your different non-static data members types and recursing over that. If your non-static data member is a class, obviously we do a recursive call. Life is simple. If it's a pointer or a reference, it's a little more complicated. And in any other case, it's probably a primitive type. It's not a class. We can check if it's a union or something. I haven't included that here. But let's say if it's an int or something. So at that point, you probably just want to hash the name of that type. And this is some feedback that I had for the authors, and we've had some discussion on it, that some name-offs should be standardized. It's a little unclear, but I can imagine that if this wasn't super standardized, things might not go well. Should work fine at the moment. I think the EDG implementation at least a month ago did not have name-off working fully for a bunch of types, but that's not the end goal. Like, that's just an intermediate state.
Does name-of give you the decorated or undecorated name?
When you mean qualified?
Name of and
Yeah.
display name of.
Yeah.
Or something like that.
yeah,
There's several different
Yeah.
varieties.
Display name-off is like an implementation-defined thing. Qualified name-off is supposed to give you with all the namespaces, and name-off is supposed to give you nothing with no namespaces. And as for pointers, this whole reflection paper also provides this const eval function substitute that can lift a function, a regular function, into reflection land and apply it on the args that you've provided. And you just remove the pointer type and hash that, and probably you put some information in there that this is a pointer, so that your hash doesn't match if it wasn't a pointer. And finally, of course, like, since you might be serializing messages, you also want to account for any padding at the end of the struct. So just hash the size of the thing. All right, so that is the end of this basic function. And the one thing that I did not include in the earlier code is avoiding cycles, because you might end up in a recursive cycle if you have pointer types. And luckily for us, ranges work. Const expr functions are nice, and we're able to do this. What you do is, if you hit a cycle, I'm proposing you just hash the index in that active types vector that you have of the types you were hashing at that given moment, and that should be good enough. Before I actually wrote this code in this value-based form, I also had a type-based implementation. And that just looks like this, where obviously you have to use something like boost MP11, but why not? Same implementation. I checked that the hash also comes out to be the same with all this. OK, so we have something that solves like 80% of some use cases. No use case is going to be solved 100% in this case, as someone alluded to earlier. But it is some improvement, I feel. Like if I had this in my ecosystem, I would definitely at least be able to solve that Python binding issue where there's a library that's coming in from, let's say, a package manager. I can't touch that. And I have to compile, implement using functions with types that are exposed by that library. And my Python binding system cannot safely cast one object to the other object because it has no guarantees about it. If we had something that works 80% of the times, that would still be like good as a whole, I think. It's a little inflexible and hard to use. That's the problem. And that's where I think I proposed this other thing called full ABI textual representation. That why don't we just serialize a JSON schema? Like JSON just being like any example syntax here. Perhaps you use an existing ecosystem like Apache Avro. I have some snippets about it later. And that way you just get a whole cross-language ecosystem. And now reflection C++ with reflection could become the one language that has the best integration with some ecosystems. Well, not the best, I'm sure other languages also have that. But you just have a struct in your type, and then there's a Apache Avro syntax representation in between, which might have forwards and backward compatibility descriptions as well, like conversion layers as to what happens if you add new fields into the data structure. And I think the right way to do this would be to use some cross-language ecosystem if we are trying to do compatibility and yeah, except for the fact that the JSON schema is going to be big. So you're not going to be able to use this in a speed-sensitive or storage-sensitive scenario. OK, so that's it for the ABI topic. And finally, I have this one thing that I was really excited to get working, was this std_any version, but better. My hope was that someday C++ could support some code like this. So this is from like 15 to 20 years ago. Like Boost Python's documentation has this example. It's a direct copy from there. This thing works in C++ because it's using Python's machinery on the other side. It's using a Py object, which is, it has nothing to do with C++, but C++ can invoke methods on it. And it has reference semantics, and you can access any attribute on the fly. It will probably throw an exception if that attribute doesn't exist. But alluding to that earlier duck typing slide, this is duck typed code. We don't really know what x is. All we care about is if y is not foo, then x should have an items attribute. That's all we want here. This is completely untyped. And why would we want this? Because if you're dealing with config files or database results or any unstructured data coming from the outside world, sometimes it's just easier to write untyped code. Like, I don't want to write an unordered map of a vector, of a pair, and so on. Similarly, there's this thing std_any, which does some sort of type erasure, but it has no duck typing. It's like a variant of everything. And also, you need to know the type that it kept into that std_any. You can't really do anything with it, but it looks nice. So what if we could combine these two ideas with reflection? I'm calling it boost virtual any. It doesn't have to be boost. But the goal is to have something like this work. I have a class. It has some methods. It has some non-static data members. I want some class called virtual any, which you can assign any virtual any to it, essentially. For instance, I'm assigning an integer to it first, and I'm able to print that. Then I'm assigning this thing called myDuck to it, and I'm also able to print things from that. So first, I want to see if we can even do this, and then we can discuss the pros and cons of this. the thing is, C++ is a multi-paradigm language, which is something that Gasper said at the last NYC++. I like that. Who are we to block this kind of paradigm? We can do this with reflection now. The way I approach this is by introducing this holding class virtual any, which has a shape pointer to a virtual any interface. So that's where it gets the name virtual from. As of right now, I just added an attribute, a call function, and a stream function to it. We could add all the other specialized operators to this, and that would not change the implementation. The idea is that any class you bring in needs to implement that virtual any interface. And we'll do that with reflection, obviously, with something like this. So in the previous example, the myDuck thing would actually create a virtual any impl with the template type myDuck. And these functions, we're going to fill these in with reflection. Primarily, the constexpr function, actually that doesn't have to be constexpr. I forgot to remove that. That getAttr function at the top, whose job is to just return a list of named attributes with this virtual any holding class for each attribute. I ended up implementing it this way. If it's not a class, then don't do anything. If it's a function, there's a function for some reason because of the call operator, don't do anything. String I had to exclude because it hit some compiler limits in terms of the constexpr number of, it hit some compiler limits in terms of how many attributes the std_string class had. It had like 270 or something, and I think there were some internal limits at 256. I haven't dug into that yet, but I just excluded this for now because I wasn't accessing any string attributes. And finally, the actual logic is just regular old reflection stuff that we've been seeing before. You do that expand, you'll go over each member. If it's a regular member, non-static data member, you just make a virtual any object and put it in there. Else you put a lambda in there that can be called. Finally, the attribute function can do whatever nice, clean things you want to do. You can throw exceptions, and you can make your code look and behave as much like Python as you want it. And the call and the stream operators also behave the same way, so there's nothing special about that. And there it is. That's all. This code works. It's nice. It's definitely different from what people are used to in C++. So this is something I do want some discussion on as to, it's slow to run, it's slow to compile. Those two are not the reasons why you would ever want to do this. There is some things I can see which, there are some benefits to this that I can see. In particular, one is that you can kind of get this duck type syntax, which is useful for operating on config files and just writing regular scratch code that a beginner might want to write at some point. The other thing that I was thinking of is if you put this thing on an ABI boundary, you could have modules be able to talk to each other when they're loading each other using a slightly more duck type syntax rather than expecting that the other side has the same unchanged ABI at the boundary of the module. That's essentially how Python modules work. Like instead of doing like a DL sim to list all the symbols in that module, Python module just opens the module, gets one symbol, and then asks it in duck syntax, hey, give me all the functions that you have or something. So you can imagine a use of this kind of approach for that scenario. What else? I think this is just, it's a fun experiment, but I do want to, I would be happy to see people come up with better usages of this. It's a very cool idea, I think. Yeah, hi.
So one comment about the ABI use case, which I think also applies to some extent to ABI, the ABI hashing thing.
Yeah.
That ABI can be more subtle than just layout, and compatibility can be more subtle than just does this have the right members. As an example, if you change the hash specialization for type, change anything about its layout or what methods it exposes. But if you have an unordered map of it exposed on an ABI boundary, and you try to access it using those two different functions on the two different sides of the boundary, things are going to go wildly wrong. So I don't think we can fully automate away the problems of ABI with these kinds of techniques.
That's fair, yeah. I think especially the fact that a hash function can just change based on those overloads. That's a fair point. That said, that's more applicable to the ABI hashing issue, I think. I think here my motivation was not to solve all issues. It was more like, right now, if you break ABI, think segfault. And with duck-typed code, if you break ABI, things throw an exception. So that's probably a little better. Oh, yeah.
Question, talking about putting it in the API and across modules or across budget, but I would be surprised if you could even pass a virtual any object across translation units, because the compiler, when you're getting the attribute or asking how it works, the compiler needs to have already compiled code for any type that you could have put in there. And a different translation unit will have get attributes that you got that'll be differently compiled in different translation units.
It should work because of the vtable though, right? There is a virtual hop in between. So all the other guy needs to know is the layout of the vtable.
Okay.
So as long as all the functions are virtual,
Yeah.
and the data types are which are eBay compatible,
Yeah.
it will work.
Yeah, that's what I thought. Essentially,
Okay,
like,
so for the different types,
yeah.
I guess what one translation unit compiles
Yeah.
gets in the object code and then gets linked in.
Yeah.
Okay.
In fact, like one other thing I forgot to put on the slide here is if, like, for instance, factory classes and stuff for dependency injection, you could compile like different versions of things that are being injected in different translation units. You don't have to keep them in the header now. And you just go through this like duck type syntax for it. It's not really adding too much. It's just helping compile time be faster.
You still do have to worry though if you have two different definitions of a type, because you're only going to end up one copy of these functions.
Yes.
Yeah.
Yeah.
You said this was slow to compile. How slow? Like your example.
This example didn't take too long. It's like 0.3 seconds or something. But I also just had like well, how many? I had like three members in this class. I should have done a bigger test. I did not, but I did check that this one wasn't particularly slow. It was like 0.2 or point something seconds on my computer. Yeah, so I thought this was very fun. I've wanted to do something like this for a while. And I guess just the last section now on alternatives to reflection, like how we've been living without it so far. Well, human reflection always works because reflection is not really anything new semantically. It's just new syntactic stuff. Humans can already do the things that compiler is now telling you. That said, we've just been paying the cost in terms of our libraries being worse. We don't have a good serialization, deserialization library that doesn't involve source in. Speaking of, source in. It's the way that our community has survived so far in this thing. Protobuf and Avro are the two that I've looked at. Essentially, you know, if you have something like this on the in Protobuf, then you just make some tool, generate that other C++ file, and link it to your code. And you get those enum to string and string to enum things. And also serializers and deserializers. Similarly, Avro, what I mentioned earlier, also has the same thing. I like Avro because it's a JSON, and we might be able to just construct this JSON when we want to. And finally, the latest form of source-in, which I've been using, is source-in with LLMs. It also just works fine. It's an easier version of human reflection. Yeah. And I think there's a few other options. I think we mentioned Boost TXT Reflect earlier. These are all limited by the max number of enumerators or max number of members that they can support. There's also this thing called class desk, which is very cool, except that I've never actually used it, so I don't want to talk about it too much. It's essentially marketed or described as reflection for C++, but with source-in itself. Like, it just takes your code and generates a richer class definition, which has reflection methods. And yeah, that's it. That's all. Yeah. Thank you, everyone. Yeah. Any questions? Hey.
So, very interesting talk. I like the subject.
Yeah.
I'm
Thanks.
thinking about the examples that you showed with the Go attributes.
Yeah.
I think it may be possible to do it with reflection, to create a struct where each data member contains the type and the compile time string.
Mm-hmm.
And then with reflection separates them into two different structs, one for the members and one for the attributes, and then map between them.
You could, yes. You could, that's an interesting idea. You take a struct, you define a new struct that doesn't have those strings essentially.
Yeah.
Yeah?
And about what you said in the end for code gen, because right now a lot of code gen has their own language and then they generate C++
Yeah.
and for other language or protocols.
Yeah.
Do you think with reflection it will change it so that our default will be to specify it in C++ structs, and then from that generate the other language, or it will stay
I think it'll change in places which don't have other languages. Like, in a big company, sometimes you might have Python and C++ and Go and a bunch of other things, and they might still keep protobuf around. But what you could do is you could have C++ generate the protobuf, which is the thing that I wanted to do with the Avro thing. Like, it's if you can just generate these JSONs from C++ structs, then you have a clean source of truth, and you can also interop with other languages. I think that's a very cool idea. And the other thing is, these kind of approaches are nicer than the ABI hashing, because even if you add a new field in there, the other side, as long as it's using Avro, as long as it's using this JSON layer to parse your message, it can still stay robust to that. But we just are using the dry principles now, so we're not repeating ourselves. Yeah. So that's very cool. There's one other downside of going through these things, though, which is that as opposed to hashing, is if the hash matches, you don't have to do any dynamic lookup of where the member is in the message. The member is there where you expect it to be, but which, at least in my use cases, since I do low latency trading, that's generally pretty important to not want to do a dynamic lookup each time you get the message. But that's why I would like a ABI hash, but not everyone needs that.
If you have a JSON schema like that,
Yeah.
adding a hash support to it is a pretty trivial.
Fair enough, except that this is big also. If you had this, then you might as well just use this, right?
Well, if you're concerned about the performance of
Right. Yeah.
quality.
Yeah, or you could just do that. The first time you get it, you can check if it's the same. And if not, then you do some dynamic-based lookup each time as a fallback. Yeah. Any other questions? Right. I guess, Finn? Yeah, thanks.